Okay. Can someone remind me where exactly we left off with C? It was the last thing we talked about.
Strings.
Okay. That would be here. Okay. Yeah, there's really not a lot left for C then. Okay, so we have notions of aggregate structures that allocate contiguous memory chunks, either via pointers or indirectly via arrays. And those contiguous memory segments can be used to represent strings. So combinations or sequences of human readable characters that are null terminated. But there are definitely other kinds of aggregate memory that we can allocate in C as well. So the most frequently used, and I think it's the most useful, is called the struct. A struct is just so if an array is a sequence of allocated memory for the same kind of data, so you have at each index, you can expect whatever variable you're declaring the array with. A struct is used to make contiguous memory allocations for differing kinds of variables. So the syntax looks like you call out the struct keyword, you give an optional struct tag. So this is effectively the name of the new type of struct you're producing. And then you have some list of variables that you're declaring. These can either be pure primitive types. They could be pointers. They could be other structs. They could also be arrays. But you declare your data type, the variable name, in whatever format you need. And basically, this ensures that your variables will be declared on either the stack or in memory generically right after each other. And so the body of the struct, just like a for loop or a function, is enclosed with these braces. And then at the very end, this is effectively your data type, right? So then you have the variable name for the struct that you're instantiating. And so I guess a more direct example would be something like this. We're declaring a book, which is a collection of information. And that information is the book's title, the author, the ISBN, and I guess I could have the book contents as well declared as part of the struct. But whenever we call out struct book, it's creating each of these variables in sequence in memory at the location where the struct is declared. There's some other syntax that we also have to provide now. So each of the variables that's declared in struct context is called a member. So title is a member of book, author is a member of book. And depending on how you declare the struct, there are two different access operators that we can now add that are struct specific. So if book is declared directly in memory, so without a pointer, then you use the dot operator to access each of the members. So a.isbn is effectively accessing the memory that's specifically declared for the ISBN variable. Likewise, if you have a pointer to a struct, then you can access it via the arrow operator. And that just means dereference the dereference the pointer and then access as if it were via the dot operator. So just a little bit of syntactic sugar to help use structs. It's kind of like objects in Python, yeah. So an object in Python is an instance of a class, and classes, by definition, are data co-located with functions that are that can operate on that data. In C, it's a little lower level than that. There isn't the notion of a class. So yeah, this is effectively just the data side of things. There is a way to do, if you have struct book, you can kind of treat it as if it's a class by writing functions that are specifically designated for it. So for instance, I could do give it a book pointer. right? So you can kind of treat this as a class because it is a collection of information, but the difference is with C, there aren't methods. So a method being a function that's associated directly with a class. You kind of have to treat it kind of by convention that this function is associated with book just because it has the name book here. But there's nothing preventing something else from calling this function, right? So it's kind of by programmer convention that you're making this entire set of statements a class, but it's not enforced by C at all. There's another C keyword that's very commonly used with like alongside struct. If you'll notice here, we have to, when doing our variable declaration, the type of the variable is struct book, and that gets kind of annoying. So in C, we can use the typedef keyword to refer to a struct with a specific struct tag with a shorthand. So again, with this book example, before I get into that, the syntax for the typedef command is you define your data type and then you give it an alias name. So it looks kind of like a variable declaration, but you're not actually allocating any memory, at least when you do the typedef. So using that book example, if we typedef struct book, so struct book and its body would be our data type definition, and then book underscore t or book type would be our alias name. And that just allows us to use the alias name directly. So every time we say book t, it's basically substituting in struct book for us. And that's just, again, by C conventions. So most frequently, I'll end up using the typedef form instead of just plain structs, because I like also being able to give this underscore t so that I know it's a data type that I've defined somewhere or someone else has defined somewhere. But you can access a typedef variable in just the same way that you would by its actual name, so by its actual type struct book. So again, we have our plain book, our pointer to book, and you can access them the same way as if it were a plainly defined struct. So now that we have all of the kinds of data you can effectively work with, I want to talk a little bit about code organization. So I didn't really get into it with assembly, but C defines clear conventions for working with projects that have multiple files. The way that C does it is each like module that you're trying to write, you typically split between two different files. One is called a header, which has the extension .h, and the other is just a source for a C file, and that has extension .c. The convention is that you usually use headers to do variable and function definitions, so not declarations. Remember the difference being a definition just declares that this thing exists, and a definition provides the full, if it's a function, it provides the body. If it's a variable, it allocates a specific memory address for that variable to be held in. So typically, the .h or the header files contain declarations only, and the .c files or the source files contain the definitions in implementation. And the reason we do this is because headers are very useful to share between different source files. So if you don't have if you have a function or a variable that's defined in another file, the file you're currently sitting in doesn't have visibility into those variables and functions. Meaning, if you try to call a function or access a variable by that name, it will be as if your current source file is the one declaring that variable or function. Sorry, if you call the function, it'll it won't build properly because it won't know where this function's memory and therefore body of statements exists. So each individual source file, if accessing a member variable or function, needs to know that that variable exists, and then somewhere else the definition for that variable or function also needs to be laid out. So you use header files to include your like your variable and function declarations so that you can share between source files, and therefore the source files can access the variables declared, or sorry, the variables, declared if they're defined elsewhere, and call the functions declared if they're given a body elsewhere, which is why headers and source files usually come in pairs. So if the header provides the definition for the variables and functions, the source file provides the implementation or the definitions. It isn't, you don't have to organize your C projects this way. If you're doing a project that only requires very simple code, it's possible to just provide one C file. And the reason you wouldn't need a header there is because you don't intend to share the contents of that C file with other source files. But typically, if your program gets large enough, you're going to want to split it out into different modules for organization's sake. It's a lot easier to maintain if you follow this paradigm as well. But if you do choose to organize your code this way, it introduces some new concepts that we have to talk about. And the first is the concept of a translation unit. So I noted if you have multiple C files, you need to have the definition included somehow of each of the functions and variables that you want to access. And the area of visibility of those variables or functions is called a translation unit. So effectively that correlates to a single source file is your translation unit. And outside of that source file, again, you need to draw in the definition or the declarations for your functions and variables before the translation unit has visibility of them. So generically, visibility of a variable or function is defined by its scope. I think we've talked about that. But the kind of the visibility of a variable or function across files is denoted by its storage class, or rather across translation units is denoted by its storage class. So what that effectively means is, yes, we can share variables that are plainly defined and functions that are plainly defined in a source file by providing a header-based declaration for each of those variables and functions. And that would be something called the global storage class, also known as the global scope. The other storage classes are auto. So I should note storage classes, they have keywords that you can apply before variables so that you can modify the storage class. It's not super common except for like in one or two cases. But I'll be referring to the storage classes by their keyword. So these are keywords that you can place in front of a variable definition in order to do this storage class modification. So auto is the default storage class for local variables. And if you've noticed, in none of the examples do I actually use the auto keyword. And that's because within the local scope, auto is automatically applied. So you don't have to worry about it. Likewise, global variables have their own storage class called extern. So this is a variable or function that's defined outside of any other variable or function. And that's kind of how we've been giving these examples. So because struct book is declared outside of a function, this would be considered a global variable. And just like auto, extern automatically applies at global scope. But you can also explicitly use the extern keyword if you're trying to access global variables that exist in other files and you don't have a declaration for them. So if I had this book type defined in, let's say, a book.c source file, and book.c didn't come with a header, but I know the variable exists because I wrote book.c, I can say in a different source file, extern book A. And now this A variable actually still has visibility in this new source file, even though I didn't share a header with the declaration. I wouldn't recommend doing this because, again, if you're sticking with the .h and .c paradigm of organizing your source code, extern kind of undermines the visibility that a header file usually provides. There are some cases where it's necessary, but for the most part, I would avoid it. The storage class modifier that is very frequently used, though, and I do recommend using, is called static. And static kind of has the ability to change the storage class of either an auto or an extern variable. So again, if the storage class is visibility to translation units, not scope, then static has the ability to change whether or not your variable is seen at global or local scope. So for more clarity, if you apply static to an otherwise global variable or an extern storage class variable, it means that the variable is no longer visible outside of the translation unit. So even if it's declared in a header, what you declare in the header is technically a new variable, as opposed to the static variable that you defined in your source file. Static is really nice for, like, if you want to have module-specific variables that shouldn't be visible outside the module. So something that is related to the implementation, but not necessarily the features that you want to expose, and you declare it as static, then that means that you can reuse the name and it won't conflict with anything outside of your module. Let's see. Yeah, so variables of the same name can exist separately in other translation units. Static also helps you indirectly shorten the length of your variable names. And the reason being is typically when you're doing module development in C, if you're being organized about it, your module has a name and maybe has structures within it. So what I would do is declare functions or variable names that have like the module name first. If these are at global scope, I would declare the module name first underscore structure name underscore function name. And that would be the full function identifier. But with static, you don't necessarily need to do that. You could just, you could say static and then your function return type in a very short function name like do something. And you can be confident that do something, when you're building your program all together with your multiple source files, that if there's a do something function declared in some other module, it won't conflict with this one. In practice, static just like under the hood renames your function to something that won't collide with anything else. And that's when you apply it to global variables. So for local variables, so that, as a reminder, variables that are declared within function scope. So something like, here we go. So this local example 1, remembering by scope rules, local example 1 is not accessible outside of this function func, but it is visible within the function. So that's, again, local scope. If you apply the static storage class keyword to a local variable, you can treat it as if it has the duration of a global variable. So it's still only visible within your local scope. But if you call the same function, the statically declared local variable will contain the same value that it ended up with when you last called the function. So in practice, what this does is instead of allocating the variable on the stack, so when you call into the function, your stack frame is produced, and then each local variable is declared on that stack, or on the stack just above your stack frame for that function. Instead of declaring the variable there, it goes and declares it in global memory instead. So just another region of memory. And that means the variable is not destroyed as soon as the function exits. Hence, being able to refer to the same variable value the next call of the function. That I wouldn't recommend using it in that manner. Really, I just recommend using static to make sure your global variables within a module don't conflict with other global variables that are defined in other modules. If you use it in functions, it kind of breaks there are certain cases where you want to make sure your functions aren't changing the state of your program. And if you're going to end up storing program state via a static local variable, it kind of breaks that assumption. So this is a technique that you can use, especially when you're just trying to bang out a prototype. But I wouldn't recommend using this in code that you're going to end up maintaining. So out of this section, static global variables are good, but static local variables I wouldn't recommend using. The last keyword I want to cover that C provides that is particularly relevant to microcontroller development is the notion of volatile. So the concept of volatility for a declared variable is that it can have its value changed without your program assigning a new variable value to the variable. And that might sound weird, like how do you get a value into a variable without doing an assignment or some operation? And there are a couple ways it can happen. So so far we've been talking about very simple computers, so single core computers that have one CPU. And that means you're running one single process. So you can only ever execute one bit of code at a time. But if your computer has multiple CPUs, so most personal computers nowadays are multi-core computers, which means they can run more than one program concurrently. If those two programs are trying to access the same memory area, so the same variable, from the visibility of one of those processes, it never touched the variable, and yet it changed its value. So we have one condition that can produce volatility. Another case, and this is the case with microcontroller development, is that you can have a hardware device that's attached to your I/O bus that accesses the variable like asynchronously. So outside of your program's access of that variable, the hardware device can be configured to like spit some result of an operation into memory as soon as it's done. And as soon as it's done could be between CPU cycles that are executing your program. And so the hardware device that your program is involved with could modify a memory address without the CPU directly accessing that memory. So the CPU has no way of knowing that the variable's value has changed. In the worst case, you're actually trying to use that variable for some kind of communication, either between processes in a multi-core computer or between a hardware device and your program. And if the CPU doesn't know that the value of that memory address or the value stored in that memory address has changed, then if you're using it to communicate, your program could miss entirely the signal coming from either the other core process or your hardware. And when you're building your code, it's even possible that, you know, if this variable doesn't have like if your program is only using this variable as a means of receiving signals, so it's never actually writing to it, if there are no branches of execution in your program that access a variable, it's possible that it'll be optimized out. So it could be represented when you produce your machine code as a constant, which is definitely not the intention of how we were going to use it, considering communications cases with underlying hardware or other processor cores. So if that variable's value never changes, then your communication will always fail. So that's a problem. And to remedy this kind of case, C provides the volatile keyword. So this is just another keyword that you can declare in front of your variable definition. So you would say like volatile int A. And what that would let the CPU know is that the memory address that's allocated when you do that full variable definition, that memory address should never be cached or treated as a constant. And that prevents the case where the CPU optimizes it out or uses a cached value instead of consistently checking the value that's stored at that memory address. So if you're using it in a communications case, again, between different cores or underlying hardware, every time the CPU wants to read the value of that variable, it'll have to check memory instead of using a cached value or an optimized constant. So that lets us say that hardware will touch that variable. So do some kind of operation or set its value. And then every time the CPU will check memory and say, okay, this variable's value has actually changed in memory. Now I can do things with it. And I'll talk about the specific cases of using volatile later when we're doing some of the hands-on microcontroller development. So apart from the use of C's variables, so these are like typed memory addresses, C also has this other notion of preprocessor directives. So you can, in one way, you can look at C as the standard that's going to produce variables that are accessible via some memory address that has a name. In another sense, C files are just text. So C has meaning to us as programmers because we can interpret the commands that we're writing, right? C has meaning to a computer only after it's been translated to machine code. So before we even get to machine code, there's this notion of preprocessor directives that basically just do text substitution. So these are programmer-specific commands that we can include in a C file that don't really have bearing on the machine code. They have bearing on the text that we write prior to translation into machine code. So I'll clarify this as we go, but the commands that you provide as preprocessor directives are called directives, and they all come with a preceding pound character or hash character. So like pound define is a very common, if not the most common preprocessor directive. And remembering that preprocessors just work with the text that is in your C file. When you say pound define label and sub, and you substitute label and sub for valid text, pound define just means that everywhere that you write the text label, that the text sub will be substituted for it before the C code is translated into machine code. So if I did, actually, I should just write if I did something like that, pound define would indicate to the preprocessor that I am declaring a new label. So this label is something that the preprocessor should look through in all of your C files. that can see this pound define. And the substituted text will be do something. Should do that. So if I have a function that I've, that I have a body for. So if I have this function definition that exists in code, if I do this, this is my plain C file that I've written as a programmer. But prior to it being translated into machine code, all of these A's will be substituted with calls to do something. So let's say, like, this is our file boundary. When it's actually turned into machine code, in an intermediate step, we'll see something like do something. How many times did I say that? Yeah. Okay. So I have the function definition and a couple labels that I've laid down in my plain C file. In an intermediate step, it will look as if I had done this. So all of these labels will be substituted with the text here, which in this case I'm using to act as if it's a function call. I would not recommend using this too frequently. What I would recommend instead doing is something like something like this, where we have a direct substitution. So pound define as a directive is very commonly used to define variable constants. So because your pound define will do a plain text substitution, when you use that pound define label in code and you do the direct substitution, this statement will equate to int a equals 5. And that means because you're not comparing it, because you're not doing this assignment via another variable, the value that you're providing via this preprocessor label is constant. So like you can't change constant name, the value of constant name, because it is hard to define prior to building your program. If this confuses anybody, I'll go into it more, but there are definitely other preprocessor directives I want to cover. So in using it this way, it's kind of const, yeah. So this pound define is not declaring a memory address. Rather, this isn't a variable. So const name doesn't exist anywhere in memory. It exists only prior to running the preprocessor. So let's say this is our entire program. All this will do is declare or is allocate memory for variable A and give it a memory address. Const name is not a variable, so it doesn't actually get allocated in memory anywhere. What const name will do is, in an intermediate step, when you build your code, the text const name will be substituted for the value 5, or for the text 5, and then your program can be built using that substituted text. Cool. It's also possible to do macros, which are like pseudo functions using define. I wouldn't recommend doing that because it gets confusing very fast. The downside of using preprocessor directives like this is that it kind of obscures the actual code. So for more complicated cases than this, you don't know whether or not const name is a substitution string or not. And the substitutions can get pretty crazy. So because this is using plain text, plain text within your source files, you can define some pretty interesting stuff that I don't want to get into because I don't want to give you the wrong idea. But know that you can use pound define very creatively if you want to. It just makes it more difficult to understand what's actually going on with the code because you as a programmer see your source files prior to the preprocessor being run. There are ways of getting around that with tools, but I won't get into it today. So some other preprocessor directives, just like we have pound define, we can also undefine an existing label. This is useful if you have a header file that you've included from another module, and it has a pound define that tramples on some symbol that you have in your existing source file. So like referring to that example, if I have const name as a pound define from some other module, but I'm using const name as a variable within my current source file, I can undefine const name, and then it won't be treated as a substituted string within my current source file. Whoops, that should be pound if. So there's a kind of a family of preprocessor directives that let you do conditional substitutions. So if else, this is effectively else if in C, and if. Collectively, these allow you to determine if the condition that's following the if or elif, if that condition is true. So if, again, it's a 0 or 1, then you do, the preprocessor does some other specific operation. So just like in C, if you have something like if 1, this could be a variable name or a label name. So okay, so these are all just preprocessor directives. And again, this all happens prior to your C being translated. So the if directive here will evaluate the condition that follows it. Here I'm using a label as a condition, but you could have like raw values that you're also evaluating here. I think there are some, there are conditions as to what can actually apply as a conditional statement here, but I won't get into all of those conditions. Here I'm just using a label that's been pound defined. So const will evaluate to 1, and so this if preprocessor directive will see that there's a 1 here, and so the preprocessor will only access the statements that are within this if body. So here, that just means that when this is 1, you'll have text substitution for anything that has the label thing A in your source code, and it'll be replaced with a 1. If I set this to 0 instead, then this conditional fails. So we go into the else body, and so thing B will be provided as a label. And anywhere that label exists, this text will be substituted with the value 2. And if, just make sure that you can close both the if or else bodies, because we don't have braces to define the bodies with preprocessor directives. I want to remind everyone again that this happens prior to your C being translated. So this entire set of preprocessor directives will evaluate to some text substitutions happening in your code, but const thing A and thing B never exist in your program memory. Is there a case where const will be a variable? So because this occurs prior to the C code being translated, you can't actually access variable values. So the preprocessor exists before you even get to having memory. So the preprocessor doesn't know when you've done variable definitions and declarations. So the preprocessor has no notion of how to interact with memory. The preprocessor doesn't even run. The preprocessor is not part of your code. So the preprocessor is a separate program that runs when you're trying to build your code. And I'll get to where that exists. But so the short answer is no, you can't use variable names here in this if evaluation. What you could do is pass arguments to the preprocessor. So like let's pretend I'm on the command line. So if there's a preprocessor that's called preproc, and that's the command for invoking the preprocessor, I could pass it some flag that says cond. I could say it's 1, and then I pass it the file that this set of preprocessor directives exists in. So file.c, and we'll say this is in file.c. So if I remove this preprocessor directive, then passing this flag, so using the D command line argument flag, then it will define cond as 1 prior to this file being active. So cond now exists as a label, and the preprocessor can then access the label. But again, all of your preprocessor statements evaluate and collapse into the text substitution prior to your C reaching translation. So the source file won't contain cond thing A or thing B. It'll contain either 1 or 2 if there are any labels in the code that you've written. I think that didn't copy paste correctly, Lucas. You might want to retype that. Let's see. So yeah, so that's another set of preprocessor directives. I'll fix the lack of pound there. There's also if defined and if not defined. So instead of evaluating a label to a value prior to doing the conditional evaluation, there's also like right, and that doesn't pay attention to the substituted value with label cond. It just determines if cond is defined at all. So even if I didn't pass a value, this if def would be evaluated because cond exists to the preprocessor, but not to C. Keep it in mind. Let's see, and the last one, and this is just after define, the most used directive is include, and that does the substitution of an entire file into your current file. So if I have, let's see, let's say I have thing.h, and thing.h includes a function definition, do something. So this function exists, doesn't have a body. And then I have .c. So just imagine these are in different files. I'm not going to break them apart. Do something, then gets its full definition, so inclusion of a body. If I have thing or other.c, If I have this other source file, and I want to call do something, other.c needs visibility of do something, so it needs to have some kind of definition for do something. And I could manually do that. So I could just write the function prototype here directly in the source file. But then if I went and changed thing.h or thing.c so that do something has a different signature, so it has like new parameters or something, that function prototype is now different, and now my code breaks. However, if I do include thing.h, what this does is the preprocessor treats everything after the #include as a file name. And as long as your preprocessor has access to the path to that file, what it'll do is take the entire contents of that file and substitute it where this #include is. So the preprocessor will manually take text void do something, stick it in other.c, and then you can build other.c, and it'll have visibility of that do something function. So I can call do something in other.c, and the preprocessor will guarantee that everything in that header file is copied directly into other.c. Let's see. Yeah, I think that's it for preprocessor directives. There will be some specific examples that I want to give for like good practices using preprocessor directives. Actually, I think we can do that now. So after last week's meeting, Alex mentioned, if there's an online program that we can use to like test C code that we write, and yes, there is. So the one I found is, called Online GDB. Stick that there and stick this over here. I'll get to what each of the things on screen mean. What the heck? Did I collapse this? Yeah, I'll get into that in a minute, but just know that here's a link. You guys can use this as a debugging tool. So to test if you've written valid C code and to determine what your C code will produce as results when it's run. So we can't necessarily use this for microprocessors for a few reasons that I'll get into today. But this is useful for testing snippets of code. So if you have like a function, you want to validate your function's behavior, you could hop on Online GDB, paste your function, call your function with some arguments, and check the resulting value pretty easily. In general, this is also a good way of checking whether or not your syntax for what you're writing is correct. So I think I'm going to do the rest of the examples within Online GDB after I get through the next section. So that was preprocessor directives. That's stuff that evaluates all prior to building your code. So anything that starts with a pound sign or a pound character is something that's seen by the preprocessor only and then substituted into your C source before the C source is translated into machine code. And I've been doing all this talking about building your program and translating a machine code, but the question remains how we actually do that. So with assembly, we had a dedicated program that did that called the assembler. So recall that the assembler just takes valid assembly text files and converts them into valid machine code. With C, we now have to have a few stages on top of the assembler because C is more complicated. So the program that actually does this translation is called a compiler. So again, it translates a source programming language into another programming language. Here we're taking our source programming language is C, and our target programming language is either directly machine code or assembly. And there are a couple of reasons for doing that. But most compilers, as they're used commonly in industry, are just used to target machine code. And you may have noticed when I pulled up online GDB, it gave us this main function that was already defined. And according to the C standard, this main function has to be somewhere in your program. So in some C file, most likely like a main.c file, you want this main function. And what this does is this function serves as the entry point to your program. So any other function call that occurs has to be branching off of main. So if I have, if I had that do something function defined, it is guaranteed that somewhere within main, if do something is called, it's within main. So main is the entry point. It's when compiled into machine code, main is effectively the first memory address in program memory for your body of code. What that means is it just gets called first. And so like your entire program needs to be either referenced or defined within this main function. There are other invocations of main that include more parameters. So there are optional parameters that you could say that main has. For microprocessors, they don't matter at all because there's no way for those parameters to ever be given a value. So I've omitted them here. But int main with an empty set of parentheses is also valid as the entry point. So if you see other forms of main, so for example, you see that somewhere, know that this is another valid function. It's another valid way of declaring main. But for our purposes, for microcontrollers, you don't need to know about these two parameters. And so we'll use the shorter form of main. So the compiler takes some C code that has main in it. It first runs the preprocessor stage. So the compilation chain is a series of programs that'll run that process your C code again and translate it into probably machine code. The first of which is a program that'll run on your computer. That's called the preprocessor. Yeah, so the argv form of main. Yeah, if you guys really want to know about it. So before I get into the rest of compilation, argc is the number of strings that argv will point to. So let's say I'm on the command line and I do, I call the program.exe. If you're on Windows, that's an exe. If you run a Unix-based machine, it'll just be program. And I pass it some arguments. So then argc will contain the value 3 because there are 3 character strings on the command line when this program is invoked. So the first argv is an array of strings. So we can look at it as if it's a 2-dimensional array or a or an array of strings. So the first dereference will get us an index into which string, and the second dereference will get us which character within that string. So again, argc is like the number of strings in this array, and then you can access the strings in the array by dereferencing argv. So that lets your program understand that there is this thing flag that I've passed to program. And in argv somewhere, you'll have, if you referenced argv1, contain that thing string. Yeah, but for microcontrollers, it is not possible for, like, you don't have a command line. The main function executes as the first thing that loads up on your microcontroller. So there's no way for argc or argv to ever contain valid values, which is why we'll ignore them for microcontroller development. Hopefully that makes more sense. Yeah, I'm trying to get through to the microcontroller theory because that's going to be the meat of what we need to talk about. So, right, compilation stages. I'm going to leave this diagram up because that does a better job of explaining things. So you have a tool chain, which is a series of programs that'll do the full compilation stages. The first is the preprocessor, and that's something we've already talked about. It is it's a program that's standalone on your computer that you run, and you pass it all of your C files that need to be preprocessed. And what that'll do is the direct text substitution for any preprocessor statement. So this is where pound includes get turned into direct file substitution in a file. So this pound include stdio.h. There's a file called stdio.h that exists, and it contains several functions that are super helpful. One of them is printf. And here I've included that header file. So our source file has visibility of all of the functions and variables that are defined here, or declared here. And so I can call them without issue. So in this case, the preprocessor will run. It'll remove that pound include standard IO, and it'll substitute it with all of the relevant variable and function declarations. So that's what the preprocessor does. And out of the preprocessor, it spits these like .i files, and that just indicates that they've been preprocessed. So this should be only pure valid C syntax without any preprocessor directives. And that's what I had been showing you before. So with the example of like that const name is 5. When I did that pound define, and I showed that the text substitution produces C code like int a equals 5 after substituting that label. Int a equals 5 is what exists in these .i files. So again, there are no preprocessor directives contained in the files that the preprocessor produces. So that's the first compilation stage. The next compilation stage is formally the compiler. So this is what does the translation of your input source files into some other language. So for the specific toolchain that I've provided as an example called GCC, which is open source and it's really commonly used in industry. For the GCC toolchain, the compiler will produce an intermediate format. So it'll do some language that's not machine code directly. And in GCC's case, it'll produce assembly. So how that's really useful is it allows you to inspect how well your program is being converted into machine instructions. So if you have a function that you're expecting to be really short, so not take many machine cycles to execute, you can actually inspect the assembly and determine how many operations it takes to equate to your function. So one thing that the compiler does is it performs some optimizations on your code. So there are many ways of converting valid C syntax into different kinds of machine instructions. So before I mentioned like for example of subroutines, you could have like a subroutine called multiply that you've defined. In C, you can have a multiply function, and without using the multiplication operator in C, you can represent this using addition. So your compiler could either recognize that you're trying to do multiplication, and if your machine has a multiplication opcode, could simply represent your function using that opcode, or it could use it. It could represent your function using a series of additions. So these are different ways that we could represent the same end result that's valid in all cases when translating C code into assembly code, in this case. But the compiler will then try to pick the one that will execute fastest. And there are a couple different conditions, so a couple different optimization settings that you can apply in a compiler to optimize for different things. So I just talked about optimizing for speed, but you can also optimize for program space. For microcontrollers, sometimes that's relevant. If you have a really tiny microcontroller that has a small amount of memory, then you don't want your program to be too big, in which case you may want to optimize for space if you have an otherwise very large program. But that optimization basically just means you're producing assembly that is tailored to either like performance or space or some other optimization target. But the compiler is doing that as it translates. Optimization also lets you prune excess variable definitions that are not actually used anywhere, or function calls that are never made, so that they straight up don't exist in the final artifact of your machine code. So the compiler is doing that for us. We can influence how it does that optimization, but in general, compilers are much better at doing optimization than humans. And so I would recommend relying on your compiler optimization rather than trying to hand optimize things. Let's see. So, right. So after the compiler produces its artifacts, these should be valid assembly files. In this case, the GCC toolchain then provides the assembler. And from this point forward, we're pretty familiar. The assembler will translate our input assembly files into valid machine code. The reason there's a little of additional complexity represented here is because for programs that span multiple files, so if you have a main.c but also a thing.c, and both of those are required to produce the functionality expected of your program, then you need a way of kind of negotiating the addresses that are used between those separate files. The reason why we can refer to storage classes as, and where the storage classes point to as translation units is for this reason particularly. So the compiler will translate one file at a time. And so it'll produce memory addresses that are used exclusively within that translation unit. After being converted into valid machine code, if you want your program to be collected into a single binary, so a single collection of machine code that runs together, then you need to kind of also translate the addresses so that your machine code from each file points to the other machine code from other files. So there's this other stage that goes on here. So the assembler produces what's called object code, which is technically valid machine code, but it also has like placeholders that allow you to substitute for the addresses referenced in other files. So typically you don't run object code because you pass it to the linker. And the linker is what actually does those substitutions of address placeholders. And out from your linker is produced the binary, so the machine code that can actually be run. So for microcontrollers, this is like the binary file that you load directly into program memory. And for personal computers, this is a binary file that you can execute. So here, this tutprog is a tutorial program from where I pulled this image. But it is a program that you can execute as soon as you perform all of these compilation stages. So in this example, you have like your main.c and aux.c, and together they form your full program logic. So the compilation stage is run, it's pre-processed, it's compiled and optimized, it's then assembled, and then linked together to form one complete position-independent binary. It's pretty common that the entire compilation toolchain, so all of these programs, are referred collectively as the compiler, even though semantically this thing is the compiler. But yeah, sometimes like we'll refer to it generically as like the GCC compiler, and we take that to mean the entire toolchain. And also the compilation toolchain generally offers a bunch of different parameters of each of these stages that you can set. So like the linker here, which does address negotiation between a bunch of different object files. You can also pass it in existing object files. So if someone provides a library that's precompiled for your machine, they can give you an object file that your linker can then link into your program if you want to refer to some function that's already been compiled, and you know that it exists in this object file. So that's an example of one of the arguments that you can pass into a linker, is like, what other existing libraries or system libraries do you want to link in? The assembler has its own options that you can provide, but it's typically fewer than the other compilation stages. The compiler obviously has optimization parameters that you can set, but there are definitely others as well. I don't actually know if the preprocessor has any other than doing preprocessor definitions at the command line. And I've been referring to the GCC suite. It's the GNU C compiler, and you can refer to all of its options, of which there are a ton. Option summary. Yeah, so for C, there's like, what standards do you want to conform to? Do you want to make sure that you don't have any inline assembly in your C? Do you want to treat character variables as if they're signed rather than unsigned? Yeah, there are a ton of options that you can pass to your compiler. We'll probably look at a few when we do the hands-on project, but I'm definitely not going to go through all of them. But you can refer to this later if you're interested. Okay, so we have our notion of computer, and we have how to program the computer, and we can use high-level languages to do so. And we now have the tool chain for working with those high-level languages. So nothing is stopping us from now getting into microcontrollers themselves. So I guess the first thing that we can do is kind of revisit our first question that we asked at the beginning of this workshop, and that's, what's a microcontroller? And before I just said it's like a really simple computer, but now we have a way of more formally understanding what a microcontroller is. So another way of referring to a microcontroller is the abbreviation MCU, or microcontroller unit. But a microcontroller is a small, comparatively low power computer, and it has dedicated I/O hardware that's generally fit for specific purposes or specific fields. Like you have a microcontroller that's for a specific engineering domain or for a specific function. And another constraint of a microcontroller is that all of it is implemented on a single integrated circuit. So I can drop down one IC without any external hardware, and it should be able to run on its own. Because microcontrollers are generally intended for specific applications, everything that's attached to the I/O bus for that internal CPU is generally a set of hardware that's, again, fit for that specific application. Additionally, the microcontroller may offer expansions to add other external pieces of electronics to the functionality of the microcontroller via its external pins. So remember, for an integrated circuit, you have signal terminals at the edge of the physical device that are called pins, and those carry our digital, or in some cases, analog signals. And the pins that are exposed on microcontrollers are usually used as the external interfaces for hardware I/O, or as a means of attaching other external electronics, like external memory and external clock, features like this. Unfortunately, microcontrollers have a ton of different designs, which means you can't just learn one microcontroller and expect it to apply to every other one. You might be able to learn the architecture, and so you'll be able to work within that family of microcontrollers, but generally you'll need to learn each family of microcontroller every time you need to do a different application that requires a different MCU. So for our project, we'll be using the Arduino Uno, which contains an Atmel Atmega 328P. So the Atmega 328P is the microcontroller. Atmega is the family produced by Atmel. And generally, each of these families has their own datasheet. So I've provided a link to that. Oops. So we'll be getting into this datasheet as soon as I get started with the project development. But generally, so you have the Atmega family, and these are the types of Atmega implementations that can be provided. All of these run the AVR enhanced RISC architecture. So this is your CPU architecture, and therefore the set of assembly or machine opcodes that it provides. So AVR is the architecture that we're working within. So we'll need to use our compiler toolchain that specifically targets AVR. So the compiler is the AVR GCC compiler is what we'll be using. And it is specifically designed to target and optimize for the AVR instruction set. Yeah, so all Atmega devices, all Atmega family integrated circuits or microcontrollers exist on the AVR architecture, and there are a couple different configurations that you can purchase the microcontroller in. So these numbers and letters following carry specific meanings that generally you have to refer to the family documentation to understand what they actually mean. So typically that's in some section called ordering information. So here, oh shoot, did they actually? No, okay. Usually they'll break it out by like what each of these signifies, but you'll have Atmega, and then you'll have some number, and then you'll have some symbol codes afterwards. So this ordering information section just tells you like what features and how much you're getting when you order a specific configuration of the microcontroller within the family. So here, we're working with the Atmega 328P. So I'm going to look for that in the ordering information to tell us what we're getting. Okay, so here's the Atmega 328P configuration down here. There are a couple different extended configuration options that you can get, and that just influences which package you're getting. So that's the form factor of the integrated circuit. It's called the package. Let's see. I wonder if they tell us. They don't break it out very cleanly. Usually they'll describe like what features are available in the specific configuration. But I guess the only way they do it here is by saying like, map these onto the various sizes offered. So here, I would guess that the Atmega 48A or PA contains 4 kilobytes of flash, and that the 328P contains 32 kilobytes of flash. So these are just, the configurations really just influence how powerful your microcontroller usually is. In this case, the memory, so the program memory and the data memory that are provided are variable by configuration. Some may offer different kinds of I/O hardware that's included in the integrated circuit. But know that we're working with the 328P configuration of the Atmega family. Reading datasheets is unfortunately one of the things that you have to get really good at to do embedded systems development, because the datasheet tells you everything you need to know about your machine. So it describes in detail the electrical properties, the programming interfaces, the CPU architecture, and basically everything you need to know to successfully program and command your microcontroller, your specifically selected microcontroller, to do some engineering task. So I spend a lot of time buried in datasheets. There are some new notions that I need to introduce as well, since we're moving from microcontrollers, from generic computers into microcontrollers. These new fields within computer architecture become more relevant. So the first feature that we need to talk about is clocking. So I mentioned when we talked about generic computers that clocking is what allows your CPU to execute the instruction cycle. So according to a clock signal, you'll step through each stage to execute instructions at a specific frequency. And also, as previously discussed, there's usually a dedicated piece of electrical hardware that provides that clock signal. Most microcontrollers provide a default clock. So it's an internal clock that's typically an RC oscillator, and that makes it pretty inaccurate. But it works if you want to only have your standalone microcontroller. Optionally, most provide the ability for you to provide an external clock, and usually that's in the form of a crystal oscillator that's much higher accuracy, so it's more stable and focused around a specific frequency. So it'll be typically more accurate than an RC oscillator. But microcontrollers also provide new options for configuring your clock. And I can navigate there, page 36. So the Atmega 328P offers the following architecture for how it manages clock signals. So we can note here, we can use an external clock, crystal oscillator, low frequency crystal oscillator, or the internal calibrated RC oscillator as inputs to our clock. So I mentioned a multiplexer. That's just you select one of the input signals as the output, and that's configurable. There's also this notion of a prescaler. So a prescaler is just an electrical, it's a digital logic block that divides the frequency of an input. So if I have one of these clock sources that's providing a square wave, then this prescaler will take the frequency of that square wave and divide it by some factor of 2 that's also configurable. So in essence, if we wanted our CPU to run more slowly for some reason, or target a specific frequency that's easier for us to work with, or it's a more stable frequency given our clock input, then I can do so by modifying the clock frequency with the prescaler. Obviously, this doesn't give us a ton of flexibility because, again, it only divides by a factor of 2. But it does let us first choose our external source frequency, and then tune it internally using a programmatically configurable prescaler value. So like a generic computer, that clock signal produces a CPU clock signal that allows the instruction cycle to execute. But also, the microcontroller will break out that clock signal to provide dedicated clocks for each of the features and functions that it offers. So in this case, yeah, Mega 328P has this module called an asynchronous timer counter, generic I/O modules, ADC, and each of these different hardware devices that are internal to the integrated circuit are provided their own clocks for various reasons. So for instance, the ADC may need a slower clock or a dedicated clock rate that's different from the CPU clock for whatever reason. So it gets its own clock signal. And typically each of these modules has the ability to configure its own prescaler as well. So clock configuration is typically the first thing I do when I'm bringing up a new microcontroller system. And by that, I mean when I'm writing an application for a specific microprocessor, the first thing I do is make sure that I'm configured for the correct clock source. And that's typically via a dedicated set of registers that help you select which clock source you're using. Usually, the microcontroller will boot up, so it'll power on and load your program and start executing instructions using the dedicated provided clock source. So it'll start with the calibrated RC oscillator, and then I'll have to configure it to whatever external oscillator we're actually using. So in this case, the Arduino, I think, has its own crystal oscillator outside of the microprocessor chip. And so somewhere in code, we would need to configure that we're using that crystal oscillator source via the clock multiplexer, and then prescale it if we want to. The other consideration with clocking is how we actually use it. So it's possible to use this clock source as to actually measure change in time within your program. The first and dumbest way of doing that is via a delay. So a delay is like a class of function that just executes for a determined amount of time and does nothing else. So this delay blocks for some period of time and prevents your program from doing other operations. The implementation usually looks like you loop over some predetermined number of ticks. So a tick is a clock cycle. And for each of those ticks, you do an assembly no operation. So a no operation or a no op is an instruction that is determined to only take one clock cycle. And also it has no side effects. So the operation does nothing. Because of this, delays are usually never the right answer when trying to determine passage of time in your program. Because effectively they just burn power. So your CPU is doing nothing as long as you're within the delay. The alternative option that I typically use that's available with microcontrollers is manually checking there's usually a register somewhere in your CPU that designates how many clock ticks have occurred. So it's just straight up a counter where the input to the counter is the CPU clock. And the way we can use that is we can measure the difference in time by measuring the difference in clock ticks at 2 different calls. Lucas is asking if this is like the millis call in Arduino, and that's exactly what I'm getting at. So the implementation here, we assume that there's this get CPU clock ticks that accesses the CPU core register containing our clock count, or our tick count for your CPU clock. And from there, it's just a simple conversion of how quickly are we expecting our clock frequency to be. And so how many clock cycles are there per millisecond? And now finally we have a function that's equivalent to the Arduino millis call. So it tells you how many milliseconds have occurred since the microcontroller got power. And so we can use the difference in calls to actually determine the difference in milliseconds that's occurred. So what that would look like in code is I would take effectively a timestamp, so the time when this function was called, and store it. And then I would do some things while I'm waiting for a time difference to occur. And then after that time has elapsed, I would do other things. So you don't have to use this form. You could take multiple timestamps and then determine the passage of time rather than doing something conditionally based on that passage of time. But generally, you want to use the form where you take a timestamp or a determination of the number of clock cycles that have occurred at one point in time and at another point in time. And that's how you would manage how did I express it? That's how you would manage referring to passage of time. Note that this probably doesn't work for long durations because regardless of how accurate your clock is, it's going to have some inaccuracy, so some instability or some variation about the target clock frequency. And that's natural, like we can't make perfect hardware. So generally, doing a delay or doing some time measurement in this manner is accurate up until a certain point. Generally, I tend to not use time measurement in this way beyond the bound of like a minute or two. And if you need to do time measurement beyond that boundary, you would typically use a piece of hardware called a real-time clock, which is dedicated hardware that is guaranteed to be much more stable than something like an oscillator. But I won't get into that because we're not going to use it for the project. The other major consideration when working with microcontrollers is power. So any computer requires power. And microcontrollers are generally rated for some kind of operating voltage range, which may be different from the logic level that the microcontroller uses. Generally, if you want to operate the CPU clock at the highest rate, so let's see. So here, the Atmega 328P documentation is saying that it can go up to 20 megahertz. Typically, if you want to do that, then you need to operate the machine at the highest input power that it can take. I don't know where. Yeah, so here the operating voltage range is defined. So again, I'm up in the features area within the datasheet. But the operating voltage range here is 1.8 volts to 5.5 volts that you can supply to the device. So depending on where you choose that supply voltage level, your logic level will also change. So if you have a supply of 1.8 volts, you can't have a logic level of 5 volts. You can only have up to 1.8 volts. So typically, unless you have a really low power application that you want to consider, which I'm not going to get into, you'll typically operate at the highest operating voltage. So here, if we supply 5.5 volts, this device will likely have a 5-volt logic level. Likewise, if you supply that 5.5 volts, you'll guaranteed be able to hit up to this 20 megahertz CPU clock. On the Arduino, there's a barrel jack. Let me, I don't know if I can. I'm not going to pull it out. I'll just scroll up. On the Arduino, there's this barrel jack. So that's a particular kind of electrical connector. And the barrel jack takes from 7 to 12 volts. That 7 to 12 volts is then fed into this voltage regulator, which regulates down to the 5.5 volts that'll supply our microcontroller. So it's pretty common for microcontrollers to have their own voltage regulation for their internal hardware, but they do have to be supplied with some kind of operating voltage. And the stages for power regulation above that often depend on what kind of board you're targeting. So if Arduino Uno is our board type, then it'll also have a 7 to 12 volt power rail somewhere on that board. I also want to take a look at the Arduino schematic real quick, just to show you, where that power regulator exists in the schematic. So these also get kind of complicated to read, so I'll point out what you need to know. But here we can see the ATmega 328P, and they use the PU package for the Arduino Uno, which is the package that looks like this. And here we have VCC, which is usually defined as the input for your operating voltage. Let's see. And so VCC is connected to our 5-volt rail according to the schematic. And because I took a look ahead of time, I know that the power supply is up here. So our 5-volt rail is generated from this NCP 111 something power supply that takes an input voltage from our barrel jack. So this is probably this is either the 7 to 12 volts or something that's been down regulated. The voltage regulator then converts that into a 5-volt supply that's very steady and provides some constant current that the ATmega can use. So apart from just consuming power, microcontrollers also are sometimes asked to supply power for applications. And I'm not sure if Alex has mentioned this to you guys, but apparently he had a project he was working on so if a microcontroller can provide power, then there's usually some specification for how much current your microcontroller can source for a given input-output pin. So in the page 308, in the microcontroller datasheet that we're targeting, I went and found the electrical characteristics. So this is like a description of all of the behavior of the external pins on the microcontroller integrated circuit. And we can see here that the current that you can supply for every I/O pin is a mere 40 milliamps, which kind of sucks. The reason this is so low is because the microcontroller is trying to keep itself low power consumption, but also because there are design constraints when making the silicon implementation of a microcontroller that if you're using small traces, so small signal carrying lines, that there's a physical limit to how much that they can heat up before they break. So for this rated current, the internal signal wires within your microcontroller are guaranteed to not break. So it's a functional limitation of the hardware itself. So if we have a high power application, so something that's going to consume much more current than this, we can't source it from the Arduino or generically our microcontroller. A specific example of this is if we're trying to drive a solenoid. So a solenoid is like, well, it's a small coil that you can energize or de-energize. And that coil will produce motion or force in a pin that travels through the coil. So a solenoid is an example of like a mechanical actuator that converts an electrical signal into mechanical motion or mechanical power. Unfortunately, solenoids are high power applications. So even if you're running them with a low voltage, they typically are high current consumers, which means in a configuration where we're driving a solenoid via a microcontroller, we need to use an external device. So if you recall, if transistors are just switches, there are certain dedicated transistors called power transistors that are capable of handling larger amounts of current. So in this case, what we would be doing is we would be sourcing a small amount of current necessary to switch the power transistor, and the power transistor is what would be used to switch the solenoid. So here we have an external power rail that we assume is capable of providing the current, enough current for both the solenoid and the microcontroller. And so it's connected to the microcontroller's input voltage pin. And it's directly connected to the solenoid. And in this case, when the microcontroller implemented on an Arduino board powers this pin, the NPN transistor will close. And so you can now flow current through the solenoid, through the transistor and to ground. And the power transistor should be able to take that amount of current. So in effect, we've buffered the Arduino from having to provide any kind of current. And this is generally how you'd want to approach any other high power application. For low power applications like lighting an LED, a microcontroller pin is probably sufficient for that. Oh yeah, as a brief note, most microcontrollers offer like a low power mode where they just don't consume a lot of current. They also have decreased functionality during that mode. But for some applications, like if you want to wait while you're waiting for some kind of external signal, and your application has nothing to do during that time, then you can send your microcontroller into low power mode while it's waiting for that external signal. So we only have about 10 minutes left. Is it okay with everybody if I go like 15 minutes over again? I would like to get through this section so that we can target the project next time.
Sounds good to me. Let's do it.
Okay. If anybody objects, the video will be up pretty shortly, and these notes are already up because I want you guys to be able to access it really fast. Yeah, we don't have too much left though. So apart from clock and power considerations, the next consideration that we have that's very common for use in microcontrollers is the notion of an interrupt. And an interrupt is a signal that exists within your machine that connects to the CPU. And when if the interrupt is configured and the CPU receives a trigger signal on that interrupt line, the CPU pauses its state and immediately jumps into an interrupt service routine. So this is a dedicated function that operates only when the interrupt trigger has been applied to the CPU. So in this way, you can interrupt the normal control flow of a program by jumping into this function, doing something, and then returning to your program. The reason these exist is like they're really useful for handling events that can't be predicted by the regular execution of a program. So for instance, if your microcontroller is connected to an external device, let's say a button, and you want to do something immediately after that button is pressed, and it's time critical that you do so, you can configure one of your pins to fire an interrupt to the CPU as soon as you detect a digital logic level change on the pin that the button is connected to. And what that'll do is, because we've configured the interrupt, as soon as you press that button, logic level changes, the interrupt fires, and then the CPU immediately jumps into the ISR, so the function that's associated with that interrupt. And so we can now take action in code immediately after that button is pressed. The alternative to doing that is polling. So it's spelled P-O-L-L. When you pull on a specific piece of information, when you pull on like a variable in memory, or you pull on the pin level in this case, you continuously try to read its current state. And so the frequency at which you read may be slow enough that there is a significant time delay between when the variable changes or when the pin level changes and when you actually read that the new value is different from the old value. So if you want to reduce that time delay between when your machine can intercept a change that you'd like to detect, you can use an interrupt. So the upside to polling is that you have a very predictable control flow, and you can handle events that are not predictable by polling. That is true, but the downside is that time delay. The upside of interrupts is that you can handle events like that immediately. The downside is it adds code complexity because now you have to jump into a function that isn't part of your regular control flow. And I'll get into why that adds complexity as soon as we get into the project. So yeah, interrupts are very good for handling time-sensitive events. Another example is if you're doing a communication and you're expecting messages to come through some interface at a specific rate. You need to be able to handle a message as soon as it comes in to be able to process it and make sure that your interface, which is accepting the messages, is prepared for the next message in time. Let's see. It's also best practice to make sure your interrupt service routine, so that function that's called when your interrupt fires, to make sure that that function is really short in execution. Oftentimes, when working with microcontrollers, you'll set up your system to have multiple interrupts configured. And in this case, if you have an interrupt that fires, so you jump into its ISR, if you take too long in that ISR and another interrupt fires, either a different kind of interrupt or the same interrupt even, then you won't be able to complete your operation in time. So you'll either miss information or you'll miss the new interrupt. And both cases are pretty terrible. So you want to generally keep the ISR to a minimum number of statements as possible. To configure an interrupt, microcontrollers often offer what's called an interrupt mask. And that's some register that if a bit identifying the interrupt is set, then it enables the interrupt. And if that bit isn't set, then even if the interrupt fires, it won't reach the CPU. For the Atmega 328P, there are many interrupts. So let's see. Page 66 defines like all of the kinds of interrupts we can have. So when these are unmasked, let's say int 0. So this is external interrupt request 0. And what this does is for a given input-output pin, if you have a signal on that pin that changes its logic level, you can configure under what conditions this interrupt will fire. But generally, if you detect a transition to logic level high, logic level low, or even on transition, you can configure this interrupt to fire. And the CPU will know that int 0 is the source, and so it'll fire the int 0 specific handler or interrupt service routine. Likewise, there are a bunch of other conditions that can trigger interrupts. So here, there's a timer counter, and when it reaches its max count, it'll overflow. And if we configure this interrupt on that overflow condition, we can trigger an interrupt to the CPU. Some interrupts can be non-maskable. So that's the notion that you can't prevent them from firing. One of them is the reset interrupt. And this is, there's an external pin and a couple other conditions that can cause your machine to arbitrarily reset. And that means it'll go back to the first memory address. It'll reset all of its internal registers, and it'll begin program execution as if it hadn't begun before. So I believe that reset is always non-maskable because the machine always needs to be able to reset. Another quirk of the Atmega 328P is that there is this there's a dedicated register that the CPU has that you have to make sure is set prior to, I think it's, yeah, here it is. So there's a global interrupt enable bit called I, and that's just a dedicated CPU register bit that enables all interrupts or none of the interrupts all at once. So you have to have both this global interrupt enable bit and the dedicated mask for your interrupt. Both of those have to be set for the interrupt to occur. It's possible to run your microcontroller without interrupts at all, in which case you would probably just clear this bit. And you can totally execute like that. But for the majority of applications, we will be using interrupts because there's typically some time critical part of an application. And the last thing of note is that because interrupts can alter the flow of execution of a program, and they can access the same memory area as your regular execution flow, then it's possible that your interrupt service routine, so that handler function, it's possible for that to write a variable value in the same memory address that your regular program can. And in that case, the variable's value will be changing without your regular program accessing it. And that's a condition where we would need to use the volatile keyword to make sure that that variable isn't optimized out or isn't cached, to make sure that the regular executing program will be able to detect the variable value change that the interrupt has commanded. So by no means have I gone through all the documentation for how to set up interrupts, but I will be getting to that as soon as we get into the project, because one of our program modules will end up needing to use it. The next feature that I want to talk about is called a watchdog. And a watchdog timer is, if you guys are familiar with the concept of a dead man switch, so something that you have to frequently service in order to make sure that it doesn't trigger. And as soon as you stop servicing the dead man switch, then some action occurs. A watchdog timer is a specific kind of dead man switch. So typically it's implemented by you needing to write to a specific register periodically. And as soon as you stop, like if there's enough time between you doing that last write to the register and the next write, or if the next write never happens, then what's called a watchdog timer, or watchdog timeout occurs. So internally, the watchdog is typically implemented using a timer counter based on the CPU clock. And if enough ticks occur between you reminding the register that you're there, the watchdog timeout will trip a specific handler. So in hardware, this will typically look like a timer counter that, when it overflows or hits some specific value that's configurable, it'll trigger an interrupt to your CPU. And that specific interrupt is the reset interrupt. So in sum, this is a dead man's switch that if you don't service it enough, your CPU will be reset. And the specific reason that this is useful is because it's possible for programmers to mess up. And if your program gets stuck in an infinite loop, your microcontroller is therefore stuck. So your application is no longer functional. You're not able to respond to any external inputs. You're just stuck. And so in that kind of case, we can use the watchdog timer to denote that the application has ceased running, and so it's critically failed. And in that case, we want to reset the entire system to make sure we can recover from that kind of condition. So presumably, when you're stuck in an infinite loop, you're not servicing the watchdog timer. And so eventually, the watchdog timer timeout will occur. The system will be reset, and you'll return to your regular application operation. And hopefully, whatever conditions caused your infinite loop don't repeat themselves. So it's kind of a safety, or it's a precautionary safety feature that lets you recover from locked up conditions. Let's see. And yeah, the ATmega 328P does include a watchdog timer that we're not going to end up configuring, mainly because we'll always have human access to a microcontroller. But for applications like in aerospace, especially when doing satellite development, it's absolutely critical to have a watchdog timer to make sure that your satellite can reboot if it gets stuck somewhere. Other applications where that's necessary, probably medical. So if you have an implant or something that's driven by a microcontroller, you never want that implant to lock up because it's very difficult to access it when it's already in a body. So yeah, watchdogs are precautions, and the typical use cases where a watchdog timer is implemented is anything that's where the machine is difficult to access or annoying to access. The last consideration that we have to talk about today, and this is the last thing I have scheduled, is how we actually get code onto the microcontroller. So when you're doing personal computer development and you're using your dedicated compiler toolchain, the output from that compiler, let's say this program. So this example, when running GCC, this toot program, this is an example for the compilation stages in producing a binary executable on your local machine. So the thing to note here is that both the compiler tools, the inputs, and the output are all on the same machine and therefore have access to the same machine memory. So when this binary executable is produced, it's just dumped in memory somewhere on the machine that it's produced on. With microcontrollers, that assumption is broken because typically you won't be doing development for the microcontroller you're targeting on the microcontroller itself. You would typically do it on your personal computer. You would produce the image that you want to have loaded onto your microcontroller, but that image isn't actually on the microcontroller. So now we need a new tool that lets us move that image into your microcontroller's program memory and data memory, depending on the contents of your binary. So in order to do that loading, we use a dedicated piece of hardware called a programmer debugger. And that connects to the microcontroller to access its memory. Typically, the microcontroller will offer some kind of standard interface. Let's see, did I mention? Yeah, 262. In this case, the ATmega 328P offers the interface called debug wire. And the interface for it is just the reset pin and the power supply to make sure that your programmer debugger can communicate with the microcontroller at all times. In this case, so these standard interfaces let you execute specific commands which the hardware on the microcontroller will then interpret to be load this memory address or erase this memory address. Debug wire has some additional features where you can do real-time control of your microcontroller. So you can analyze the register values, the memory values, and set them. You can individually step through instructions. So you can stop the CPU clock and instead only execute instructions when you command over the debug interface. So debug wire specifically for the Atmega 328P allows us to basically command and control the entire device, in addition to programming the program memory and data memory segments. So this debug wire connection would have to be to some external physical device that connects to your personal computer. So that external device is like a bridge between your development environment on your PC and the microcontroller via this interface. There are other programming interfaces that we can use. So the other one for the Atmega 328P is called AVR ISP. So that's in-circuit serial programming, so ICSP, sorry. And it's just a serial communication that only offers commands for accessing memory. So you can't really do debugging over this interface. But it is another interface that provides a different format that maybe another machine can use. And I want to show you where those are connected on the Arduino schematic. The last kind of option that we have for getting code loaded onto our microcontroller is by using a bootloader method. A bootloader is it's a series of machine instructions, so it's a specific application that comes preloaded on your microcontroller. And that application is a program that'll start immediately on boot, hence the name. And it allows you to use non-hardware supported interfaces. So for instance, for the Atmega 328P on the Arduino, if I loaded a custom bootloader on there, and the bootloader says, we can now let you use pins PB0 and PB1 as communication interfaces to communicate your program information. Then the bootloader would load as soon as the system receives power, check on those interfaces and maybe wait for a signal or something. And if a signal is not received, the bootloader would then just begin the program that's actually loaded. So it would jump into a different segment of program memory and start there. And the bootloader knows when it's copying your program onto the device, where it's storing the program that you want to load. So in this case, the bootloader and your program are both loaded onto your target microcontroller if you choose to use a bootloader. The Arduino has a weird configuration for a bootloader. The Arduino actually has a secondary, let me actually show you. The Arduino actually has a secondary microcontroller that allows bootloading over USB. So this configuration is, there's this big USB-A connector that you can connect to, and you can send your program information and commands to this microcontroller, which then acts as a bridge by driving the target microcontroller. So this microcontroller interprets the commands coming in and does the direct programming of the microcontroller our code will actually run on. So this microcontroller does not run our code. It only acts as the bootloader. And this microcontroller actually runs our code, but is bootloaded by this other microcontroller. And I can show you exactly where that signal happens. So here in the electrical schematic, we have our USB signals, data positive and data minus are fed into this secondary microcontroller. this secondary microcontroller then takes action based on the information that's communicated to it. And it drives the reset signal on our target. So recall the debug wire interface operates exclusively on the Atmega 328P's reset pin. So the debug wire interface has a connection to this secondary microcontroller via the reset line. And that allows the dedicated program that's running here to use the debug wire set of commands to load our program. Unfortunately, because the interface that we will be using to program this device is via the USB bootloader. That means we don't have access to the complete set of commands that debug wire offers. So we won't be able to do that like live stepping through code on an Arduino board, unless we were to connect a dedicated programmer debugger. I figured programmer debuggers are really expensive and I didn't want you guys to have to buy that. So for our examples, we'll just be using the USB bootloader, but it will make debugging a little bit difficult. And I wouldn't recommend using a bootloader method until you have your application code fully debugged. So in practice, it would look like you would get your new board in, you would connect your programmer debugger, load code that way using that method, and do your debugging. So via, in this case, the debug wire interface. I believe, yeah, this ICSP header here, this collection of pins, one of those is the reset pin, or connects to the reset pin on the microcontroller. And so if you have a programmer debugger, you can still use debug wire, but it has to be over this interface. Again, we'll be using the USB bootloader interface for all of our interfacing with a machine. Let's see. Yeah, so that's a really quick overview of how programming will occur, at least for the project. And then I'll get into the tools that we're actually going to use to do so. The software tools, that is, on our personal computer, that'll allow us to communicate over USB to the Arduino bootloader as soon as we get started on the project. So to wrap it up, next time we'll be getting into, I'm going to talk about the project architecture, knowing what we know now, and then I'll get into the implementation of the project software, which will touch on the internal hardware components that we're using on the Atmega 328P, and the development process that we're going to use, and the tools and all the methods for actually developing that code, deploying it, and then testing our project. In order to do that, I highly recommend you guys follow this checklist for downloading and installing all of the tools that we're going to need that I'm going to demo next time, and if we run over another workshop the time after that. These notes are already up, so this list should be available now, and you can check on that. So AVR Dude is the software program. It's the PC-based program that lets us communicate over USB to any AVR device. In this case, it knows about the Arduino bootloader and can speak to it. So this will let us load our program onto our target Atmega 328P. The AVR Dude requires an Arduino specific config file, which either I will provide you directly via the website, or you can download it at this link. The AVR 8-bit toolchain, so that's the compiler and all the other associated tools that are necessary to build C code, which targets an AVR device. M-file, this tool produces makefiles, which are like collections of commands that we have to run very frequently. So I'm going to use makefiles to generate the commands that we need to do a full build of our project and to do uploading to the Arduino. And these last three are project specific. So if these first four are all the tools that we need to do development on a generic microcontroller that is using the AVR architecture, these three let us do things that are specific to the project. And I'll get into why we need them as I describe the project. So that's all I got for today. Thank you guys for bearing with me. And next time, like I said, we'll get into the project itself, and hopefully it'll be more hands-on. Are there pressing questions that I should answer before we sign off? So maybe about the data sheet, how to interpret it, how to find things, or how to read the schematic, or any of the microcontroller features that I talked about today.
I'm assuming we'll kind of get into that, I guess, next week as we're like using that sort of stuff. But yeah, what's up, Riley?
So it says like the loop MIDI is for Windows users only, and I only have a MacBook, so
you don't need loop MIDI then.
I don't need it all. Okay, cool.
Yeah.
Okay, awesome. Thank you.
Mm-hmm. I would also recommend, if you guys haven't started like independently looking at C, I would recommend either refreshing yourself via the workshop notes on C, or via online tutorials, and maybe using online GDB to like test that code that you're writing. The only requirement is that you guys can read it by next time, because I'm going to be stepping through each of the project source files to describe what's going on, both at a software level and at a microcontroller level. So it would be really helpful to be able to be C literate by that time. A generic understanding would be sufficient. So you don't need to be able to reproduce it by any means.
Sweet. All right, well, if that's everything, then yeah, I guess we'll continue next week. Looking forward to this.
Yeah,
thanks, Michael.
Great. Sounds good to me.
Thanks everyone for coming.
Yeah.
Thank you. Thank you.